Hello students, this is Ishan Akbar. In this video lecture, we will discuss that how can we find out the stress increase below a point load in one direction. It means that we have only one direction in our question, means that is a horizontal direction, and a load is applying on the soil surface, and we want to determine its impact on any point which is below the surface of the earth or surface of the soil. So let us say we have this as the ground surface. This line shows the ground surface, and a load is acting at this point or at any point on the surface of the soil. So say this is the point A at which the stress or load is a load is acting in the form of a point. Means say this is a point load P and is equal to 1000 kilonewton, and we want to determine its impact on any point below, that may be a point B, that is exactly below the vertical line of this load. You can see here the load is acting at this point, and this point B is exactly vertically below this point. So we can say that this is a one dimensional question. So we have only one dimension or one direction to solve this question, that is the only vertical direction. To determine the stress at this point B, we can say that as the stress increase, that is known as the delta sigma Z. At this point, we want to determine this stress increase at this point. So what will we do? We will determine the vertical distance between the both points. Say this distance is 8 meters between both the points. So basically, we need the direct distance. This Z is the direct distance between point of application of load and the point at which we want to determine the stress. This is the direct distance. So don't remember this Z, only remember the direct distance mean a straight line joining the point of application of load and the point at which we want to determine the stress increase. So simply, this is a simple procedure to use this direct distance as 8 meter and the vertical direct distance as 8 meter, because both are same. Vertical distance is also 8 meter and the direct distance is also 8 meter, because the point of stress lies exactly below the load point. So basically we use the basic formula to determine the stress increase due to point load, that is 3 3 times P. The P is applied load, Z raised to power 3. Z here is the vertical distance between the points, and 2 pi R raised to power 5. So this R is the direct distance between the points. So in this case, we only have one distance. In the next case, we will have two distances. I will let you know the difference between Z and R. Here, Z is equal to R because we have only one D case. Always when you are dealing in one dimensional or one directional case, you will assume that R is equal to Z, because this Z is also the vertical distance between the points, and this is also the direct distance between these points. So Z and R both are 8 meters. P is 100 kilonewton, so we'll put P as 1000 kilonewton. Z is 8. What is R? This is also 8 in this case, and pi is 22 by 7. So when we put these values in the formula, we'll get the desired result. 1000 kilonewton into Z is 8 meters raised to power 3 divided by 2, 22 by 7 into 8 meter raised to power 5. So when we calculate these numeric values, we get an answer of 7.46 kilonewton. This one, meter raised to power 3, this will be meter cube, and meter raised to power 12, this will be meter raised to power 5. And when we cancel this, we will only get meter square in the denominator. So delta sigma Z is equal to 7.48 kilonewton per meter square, or we can say 7.48 kilopascals. This Newton per meter square is equal to Pascal. So simply we can say that stress increase below a point load at a vertical distance of 8 meter is equal to 7.48 kilopascals. You can say this as 7.5. So in the next, this was the case of 1D, mean we have no horizontal movement or no horizontal dimension. So in the next case, let us say we have this soil surface and we have a point at which a load P is applying. The same load we can say that is 1000 kilonewton, and we want to determine a stress at point this point is now B, this point is A. So in last case we had point at this location, but now it is shifted towards location B. We have a vertical distance of this point, this is equal to Z, say this is 8 meter, and we also have a horizontal distance because point A and B are located at some horizontal distance. This will be known as the small r. Say this is 7 meters. So we can say this is a 7 meter length. So for this, see here, for Z and R, Z is always the vertical distance. Z is always the vertical distance while R is the direct distance here. So we are interested in both of these values in Z and R because for the formula in this for the stress increase we have both these values 3p z cube divided by 2 pi r raised to power 5. So we need z and we need r as well. So we want to know both of these, that what is z and what is r. Z is basically the vertical distance between the load point to the point of stress increase. We will draw a horizontal line from the point of stress increase, and when these points cut each other, we will determine this vertical distance. And in this question, this distance is 8 meter. And again, we will measure from this vertical line to the stress point. We will determine the horizontal distance, and in this case, it is 7 meters. So we want to determine basically the stress increase at this point now. So our next point of ponder is to determine this direct distance. So this is the vertical distance called Z, and this is the direct distance called capital R. So we have to determine this R. So R is equal to, we know this is our right angle triangle. This is the hypotenuse. So to determine the hypotenuse, we have the Pythagoras theorem, that is equal to perpendicular square and base square. This perpendicular plus base square root gives us the value of hypotenuse, which is R in this case. So 8 meter square plus 7 meter square with square root will give us the value. So it will be 64 plus 49 square root. It will be 10.63 meters. So we have value of R as 10.63 meters. So in this case, we have 8 meter. Z is the vertical distance. This is 8 meters. And R is the direct distance. That is 10.63 meters. So we want to put these values in this formula, and we will get the stress increase below the point load in two dimensions, because we have a dimension is along the y-axis and a dimension along the x-axis. In the previous case, we only had a dimension in one direction, mean this was only in the y direction. So we called it as 1D, but in next case we have 2D problem that is in two dimensions. Mean this is also covering the, sorry, y-axis and also the x-axis. So we will put the values of P as 1000 kilonewton, Z as 8 meter raised to power 3 divided by 2 times 22 by 7 as pi, and R is 10.63 meters raised to power 5. When we simplify this formula, we will get the answer as 1.80 kilonewton per meter square. So we can simply say that the stress increase below this point is 1 point below this load of 1000 kilonewton at a point which is vertically 8 meter and horizontally 7 meter from the load point. 80 kilopascals. So in this way we can calculate the stresses at any point below the loaded point. So what what did we observe from these two points? In first case, we had this as the point of ponder. Mean this was our point to determine the stress increase, and we got a stress of 7.46 kilonewton per meter square. And at this point, the stress is 1.8 kilonewton per meter square. So what is the difference? This stress is greater than this 1.8. It means that whenever at a single depth, at a same depth, when you move horizontally away from the point, vertical line of or vertical point of the load, then the stress will decrease. So basically, we follow a pressure bulb. We have seen in soil mechanics this type of pressure bulb. The stress increases to a maximum value and then starts decreasing. And then on the horizontal sides, the same trend is observed that first the value will increase and then it will decrease. The maximum stress due to this point load will be maximum exactly below the point. And say we want to determine the stress at this point at 4 meter depth, so we will have maximum stress at 4 meter exactly below the point. And when we will move in this direction, let us say this stress is 3 kilopascals. It will be 2. At this point, it will be 1. At this point, it will be zero point 0.5. At this point, it will be 0.25. And we will reach a point at which the stress increase will be equal to 0 kPa. So for every distance, we have a different point location horizontally at which the stress will become zero. And with the help of those values, we get a stress bulb. I think you will like my video. If you like my video, then please subscribe my channel and recommend it to your friends. Thank you very much for watching. Take care.